Okay, I think we are good to go. I'll wait maybe for a couple of minutes, okay, if somebody wants to join. Otherwise, we can go ahead. Okay, just we're gonna wait a couple of minutes. Yes, so okay, let's start. Okay, so in this week's assignments, okay, it's mostly the questions is mostly related to your magnetisms. Okay, I'm sure that you have heard about diamagnetic materials, paramagnetic materials, ferromagnetic materials, and so on. If you can refer the details of those derivations and so on, you can always follow Ketel textbooks, right? It has all the details in it, okay, especially your magnetism portion. So but in this course, I mean, especially in this tutorial, we are not going to derive the derivation and so on, okay, because that will take a lot of time, okay. So I'll mostly show you uh, the solutions, or the how to solve your tutorials, I mean, and the questions, okay. So but maybe let me just give a little of a brief just introductions of your magnetisms. So when you talk about magnetisms, okay, what does it mean? Suppose if you place a solid, any solids, place inside a magnetic field, what will happen? It gets magnetized, right? This is a simple. Okay, so that means if you place a solid inside a magnetic field, what will happen to the solids? It will get magnetized. So there are different types of your magnetisms. If you, I mean, if you have seen it, you are talking about your diamagnetism. Diamagnetism means those metals which do not have your permanent magnetic moment. Okay, but if you have an external magnetic field, then the solid will get, or then your diamagnetic metals will get magnetized. Okay, that is called a diamagnetism. The second is your paramagnetism. Paramagnetism also, they have a permanent dipoles, but the problem is that with the paramagnetism is that because of your thermal energy, all these magnetic moment cancel one another. But now if you apply magnetic field, then you will have a certain dipoles aligned in a certain directions, okay, along the direction of the magnetic field. Then you will get your then you will get then your metal will get magnetized. And last one is last, I mean, there are many, but ferromagnetisms, they are those metals which inherently have its own magnetic momentum moment. Okay, so that is your ferromagnetic magnetisms. Okay, if you want all the details of it, you can follow this Kittel textbooks, okay, about what is a diamagnetism, what is a paramagnetism, and what is a ferromagnetism. But simple idea is that diamagnetisms materials are not magnetized on its own. We have to apply a magnetic field. Second is paramagnetism. Yes, they have its own dipole moment, but the problem is because of the thermal energy, they cancel one another, and as a result, you have a zero magnetic moment, or you have a zero magnetization. I would let to say, okay, zero magnetization. Ferromagnetisms is they have a certain inherent magnetization on its own because of its intrinsic magnetic moment. Okay, so if I write magnetic moment per unit volume is called magnetization. Okay, from now onwards, we will be talking mostly about magnetization. That is, what is the magnetic moment in the solid per unit volume? Okay, so that is what is called as a magnetization. And another concept which is also called as susceptibility. Susceptibility is psi is equal to magnetization per unit applied electric field. That means how much you can magnetize a material with 1 unit of external magnetic field. So the stronger the susceptibility means the stronger is the magnetization, right? So different materials have different susceptibility. That means if you apply 1 unit of external magnetic field, how much you can magnetize a material. Okay, that is what is susceptibility means. Now, there's also some relations and formula which I can write it here. B is equal to mu naught of H plus of M. Okay, here H is your magnetic field intensity strength, B is your magnetic flux density. I can write magnetic flux density. Yeah, M is your magnetization, M is your magnetization. Okay, H is your field strength. Now, or I can also write as B is equal to the same relation, B is equal to mu H, which means that mu is equal to mu naught mu r, and mu r is equal to 1 plus of psi. Why? Is because you substitute here m is equal to what, psi of h, and you take common of it, you will get B is equal to mu h, where mu is equal to mu naught mu r, and mu is equal to 1 plus of psi. Okay, this is some of the formulas that you might already seen, or it also will be helpful to have a look at it. Okay, so yeah, next we will look at your diamagnetism part. Okay, what is most important in the primary part is this: there is no permanent magnetic moment. Okay, there is no permanent moment. And the second one is your magnetic moment is induced magnetic moment induced is opposite to the applied magnetic field. Okay, just I have mentioned to you that just like I have mentioned to you that your diamagnetism, in the diamagnetism you have no permanent magnetic moment, but your magnetic moment can be induced by the applied external magnetic field, and that induced magnetic moment is opposite to the applied magnetic field. So if I have to quantify the induced magnetic moment, I have to write the susceptibility psi. Just like I have mentioned to you that susceptibility is in fact related how much magnetization you get per unit applied magnetic field, external magnetic field strength. So here also psi is given to be minus n mu naught z e square by 6m and average of r square. Okay, this is your formula for your diamagnetism. And how do I get this one? You can follow Langevin formula. Okay, Langevin formula from your Kittel, you will get the relation. There is a derivation for this diamagnetic materials, and the final expression is psi is negative. Remember, this is negative. Okay, negative means opposite direction, and also it is inversely proportional to the mass, and it's directly proportional to the number of atoms. Okay, Z is the atomic number, mu naught is your susceptibility, permeability, and E square is your charge, and R square is average distance. Okay, so that means remember that your susceptibility in this case that is negative. Okay, so if you look at the first problems, so I will solve your questions. Number one, what does it say? It says that calculate the diamagnetic susceptibility of atomic hydrogen. Calculate the diamagnetic susceptibility susceptibility of atomic hydrogen. Okay, of atomic, remember, of atomic hydrogen in the ground state wave function given by what? Psi of r equal to 1 divided by root over of pi a naught to the power cubed exponential of minus of r divided by a naught. Okay, so what is it? What do you have to find out? You have to find out the diamagnetic susceptibility. And diamagnetic susceptibility is given by this formula. Psi is equal to minus of n mu naught z is squared by 6m into the average distance. Okay, r square is average distance. Now, what is also given to you, according to the problem, is given to you the wave function psi, and you have to calculate the diamagnetic susceptibility of a hydrogen atom. Hydrogen atom means your z equal to 1. Okay, and also given to you a naught, which is the lattice constant, is 0.46 Armstrong, and n is 2.69 into 10 to the power 28 per meter cube. Okay, this is also given to you. That means if you look at the above formula, n you know, z you know, mu naught you know, e square you know, 6 you know, m you know, and you have to find out what is the r square. That is only quantity here which you don't know at the moment. This r square. Okay. Now let me just remind you, how do we get this psi of r? If you go back to quantum mechanics in the last few tutorials, you will have seen that your ground state of a hydrogen atom is 1 by root over of pi a naught cubed is equal to r divided by a naught. Okay, this is very important. Sorry, this a naught is your Bohr's radius. Okay, not your lattice constant. Sorry, I misinterpreted. Okay, a naught is your, I was saying a naught is a lattice constant. No, it's actually the Bohr's radius. Okay, so because it is a hydrogen atom and your ground state that is given by psi of r is equal to 1 by root over of pi a naught cubed exponential of minus of r divided by a naught. Okay, and if you want to know from where this formula, you can go back to your hydrogen atom from quantum mechanics. Okay, from quantum mechanics, if you want to get back to this. Okay, but at this moment you just need to know that this equation is already given to you and represents the ground state of a hydrogen atom. Okay, fine. So what I have told you is that we need to, out of the formulas which we have already seen, minus of n mu naught z is squared by 6m, what is the one quantity that you don't know is r square. So anybody have any questions? Can I mute this one? Yeah. Fine. Now, what I will do here now is I will try to solve what is this r square term here. Okay, such that we can easily calculate your susceptibility. So to calculate, so the first part I will be doing is, okay, I will write here the formulas of psi. I will write the formula of psi. What you have to solve is minus of mu naught n z e square by 6me into r square. Okay, now the first thing that I will solve is I will try to solve what is your r square term. Okay, so for atomic hydrogen atom, in the ground state, okay, that means in the ground state of hydrogen z is equal to 1 with psi of r equal to 1 divided by root over of pi a naught cube e to the power minus of r divided by a naught. The expectation value, that means your r square, the expectation value r square can be written as r square equal to integration of your wave function psi complex conjugate r square and psi dv. Okay, this is what this psi is a function of r. Okay, so we can solve these problems in terms of spherical polar coordinates. Okay, and we can write in terms of r, theta and phi. So you will get 0 to infinity if I want to integrate it, and 0 to pi for your theta part, and 0 to 2 pi for your phi part. So if I want to write this, since psi here appears two times, I can just put a square term which is equal to 1 divided by root over of pi a naught cubed e to the power minus of r divided by a naught whole square. Okay, and then r square will be there as it is, and this dv in terms of spherical polar coordinates is r square sine theta dr d theta d phi. Okay, so I convert everything in terms of your spherical polar coordinates. Okay, and now you have if you look at it, sorry, if you look at it, this 1 by pi a naught cube anyway is a constant, so you can take it out. With the square term, you can easily get 1 divided by pi a naught cubed. Okay, so the integration remaining is 0 to infinity of e to the power minus of 2r divided by a naught. Okay, that is one term, and r to the power 4 dr. That means you separate all the r term separately, theta term separately, and phi part separately. Now your theta will become 0 to 2 pi. Okay, and there is only sine theta here, so get sine theta d theta, and the phi part 0 to 2 pi of d phi. So this integration is a standard integration. I can just write it in this terms of the formula: 0 to infinity of x to the power n e to the power minus of a of x d of x. Okay, uh, hello, am I audible to you? I think there is a, sorry, there is a problem, network suddenly in my line. Uh, yeah, so sorry. Okay, there is a problem with my line from this side. Okay, there's power shut down suddenly. Then let me just try to reconnect it again. Yeah, so am I audible to you? I think so. Sorry for the network problems. It has never happened. Uh, yeah, okay, so let me just try to do it whether it's possible or not. Okay, so let me reconnect it. The Wi-Fi is back. Yeah, so again, so sorry. Let me just reset up again. Yeah, okay. Am I still audible to you? Uh, Okay, so yeah, thank you for your patience. Okay, there was a there was a power shutdown, then suddenly it goes down, all the internet and then Wi-Fi connection goes suddenly. Okay, so yeah, okay, so let's start. Okay, I mean let's continue. See, I have just mentioned to you that how do we solve your susceptibility is already given to you. I mean, from the diamagnetisms, you can see calculate the diamagnetisms which is proportional to your R square term. But since in this formula most of the terms are already constant, you just need to calculate what is your R square. And R square from quantum mechanics says that your expectation value is actually the product of your psi star, psi as well as what do you want to calculate R square. Okay, this is from your quantum mechanics. Okay, expectation value which we have already seen in the previous tutorials. So now we have to solve this integration 1 divided by pi a naught cubed 1 divided by pi a naught cubed e to the power minus of 2r divided by a naught r4. This is the standard integration. If you use this formula, x to the power of n e to the minus of ax is equal to what? Is equal to n factorial divided by a to the power of n plus 1. N factorial means this case and a is in this case. Okay, so in our case, n is what? N is equal to 4, right? This is our case, n is equal to 4, whereas a in our case is 2 by a naught, right, in our case. So you can use directly the standard integration, or you have to do the product integration, okay, which is very lengthy. So if you know this standard integration, you can just directly substitute that what is the value of n, what is the value of a, and then you know what is it, the whole integration. So now what happens, you get r square is equal to 4. Before that, let me just write this here. R square is equal to 4 divided by, 4 divided by a naught cubed. Why 4 divided by a naught cubed? Because this integration is equal to 2, and this integration is equal to 2 pi. Okay, sin theta d theta, the integration from 0 to pi will give you 2. The integration from 0 to 2 pi of d phi will give you 2 pi. Okay, so the whole integration will become 4 by a naught, and then integration from 0 to infinity, r to the power 4 e to the power minus of 2 r divided by a naught d of r. Okay, so that means sin theta d theta, this term you already know. And integration of d phi is the standard integration, which is equal to 2 pi. Now if you substitute whatever the standard integration in this formula, you will get 4 divided by a naught cubed, and we'll have 4 factorial, because it is n factorial, divided by 2 divided by a naught to the power n plus 1, so you'll get to the power 5. Okay, so how did I get this integration? 4 factorial divided by 2 of a naught to the power 5. I just make use of the standard integration which is already there. N is equal to 4, a naught is equal to 2 by a naught, and you use this integration n factorial divided by 2 divided by a to the power of n plus 1. Okay, so now this is very direct. Now you will have 4 divided by a naught cubed, and this integration will be simply 24 a naught to the power 5 divided by 32, and finally you have 3 a naught square. Okay, so what happens is that now yeah, so now you know now your average or your expectation value of r square, and you can substitute directly psi equal to, in the main equation, minus of mu naught n. Z is already equal to 1. Remember, Z is for hydrogen atom, atomic number Z is equal to 1, so you don't need to bother. E is equal to e square divided by 6m, and what is the value of r square? 3 a naught square. Okay, so now let's look back. What is a naught? A naught is equal to 0.46 Armstrong, which is equal to 0.46 into 10 to the power minus of 10 meter. N is equal to, is given to you, 2.69 into 10 to the power 28 meter cube. Mu naught in SI unit is equal to 4 pi into 10 to the power minus 7 in your SI unit. And finally you have E is equal to 1.6 into 10 to the power minus of 19 coulomb, and ME you can use 9.1 into 10 to the power minus of 31 kg. So if you substitute all these formulas, A naught, N, mu naught, E, Me, so what will happen? Psi, which is negative, okay, which is negative, you will get 4 pi. I'll just substitute 4 pi into 10 to the power minus of 7, one thing. Second is 2.69 into 10 to the power 28, that is your N, carrier concentration or carrier density, into 1.6 into 10 to the power minus of 19, this is your E square, and your R square is 0.46, sorry, A naught square is 0.46 into 10 to the power minus of 10 whole square divided by 2, because 3 and 6 will get cancelled, you get 2 into 9.1 into 10 to the power minus of 31. Okay, so if you solve this if you solve this multiplication and squaring, you will get approximately minus of 1.0, let's say minus of 1.01. Okay, so so in the first questions, okay, we have to solve what is the susceptibility, and now that this is your answer, susceptibility. And in those questions, what you need to find out, you need to find out only your r square, which is equal to 3a naught square. Okay, so once you do the 3 on the squares, all your mu naught and e square are they are constant values, so you don't need to worry anything. You just need to solve what is the expectation value. So once you know the expectation value, then you can calculate what is the susceptibility. And remember that your susceptibility is negative. Okay, your susceptibility is, for a diamagnetism, the susceptibility is negative. What does it means? It also means that your magnetization, as I've just mentioned, that your susceptibility is directly related to I mean the main equation, your susceptibility is directly equal to your magnetization. So if your magnetization is negative, then that means your susceptibility also is negative. Okay, fine. So this is a very standard problems. Now there is another questions which is related to your paramagnetic, which is question number 2. Let me just check question number 2. uh, yeah, okay, so let me solve the question number 4, which is also interesting. So, okay, so question number 4, before I solve question number 2 and question number 3, let me also solve question number 4. Okay, so in question number 4 is what is I mean the question is asked how many possible spin orientations are possible combining two s particle, s is equal to half particles, and what are the states called? Okay, so this is very interesting problem, because suppose if you have two spins, okay, two particles, let's say two particles with spin half, okay, what are the possible states that these particles can be? Okay, so that is the question, what are the possible and what are the states called? Okay, so you have to write out what are the possible states that these two particles can have and what are they named. Okay, so what happens is that, so when you have s is equal to half, okay, and when these two particles combine, when combining two particles, when combining two particles, let's say with spin s1 equal to half and s2 equal to half, right? You have two particles. Let's say the first particle has spin 1, s1 is equal to half, and also s2 is equal to half. Then what will happen? The total number of possible states, the total number of possible states is what? Is n equal to, it's a product of the 2 s1 plus 1, 2 s2 plus 1. So since s1 is equal to half, so you get 2 into half plus 1, and also 2 into half plus 1. You will get 4 possible states. Okay, so these are the states that you are expecting, 4 possible. It is given by the product of 2s1 plus 1 and 2s2 plus 2. Okay, these are the, but what are those states? Okay, so the states, okay, what are the 4 possible states? The 4 possible states are given to be, the first one is the singlet state. Okay, or I would rather say that I will divide these one into 2 groups. Okay, the 4 possible states can be divided into 2 groups. The first one is singlet state. Okay, so in a singlet state you have what? A singlet state, a singlet state is 2s plus 1 equal to 1 with capital S equal to 0. This is very important. Okay, what is a singlet? A singlet state is means that the total spin S should be equal to 0, such that the product 2s plus 1 equal to 1. This is called as a singlet state. Okay, and how do they mean? It also means that these are anti-symmetric under particles exchange. Okay, s equal to 0 means what? They are of opposite spin. Okay, well, capital S equal to 0. Suppose we have s1 is equal to half and s2 is equal to half, and if you combine them together, what will happen? There are four possible states in which they can interact. Okay, so the first one out of the four possible states, the first one is called as the singlet state. Singlet state means both the spins are opposite, such that the total s equal to 0, and if you calculate 2s plus 1, you have equal to 1 state. Okay, so 2s plus 1 is equal to 1 with the total spin capital S is equal to 0. Okay, that is the first. That means you have one state here, which is called as a singlet state. Two is called as a triplet state. Okay, in a triplet state, what happens? There are three states in the triplet states. That is 2s plus 1 equal to 3 with total spin s equal to 1. What does it mean s equal to 1? In the first case, singlet state, you have opposite spin. That is why you have s equal to 0. The total plus half and minus half, they cancel one. You have s equal to 0, you have one possible state. Whereas in the case of a triple state, since you have s equal to 1, that means they are either parallel or anti-parallel. But that means they align in the same direction. That means if I want to say they are symmetric under particle exchange. Okay, so we will see further. Okay, we'll see further. But if we have two possible particles with this two spin half, with spin half, that means s1 is equal to half, s2 is equal to half, then what happens if we interact them together? If we combine two particles, then we'll have the total spin. Okay, they can either be parallel, they can either be anti-parallel. Okay, they can have plus half plus half, or plus half minus half, minus half half, right? Minus half, and so on. But out of the four possible states that you can get given by this equation, n is equal to 2s plus 1 and s plus 2, and 2s2 plus 1, it can be divided into four states, and those four states are classified again into singlet state and triplet state. Singlet state means only one, and this is obtained when you have spin of opposite. Okay, that is why your anti-symmetric particle, that means you have anti-symmetric under particle exchange. But in the singlet state, since the particles have this or I can say plus half, that means you will have s equal to 1, then the total will be equal to 3. Okay, and also they are symmetric under particle exchange. Okay, fine. So that means if you have two particles, you have four possible states. And the question number 2 is calculate s1 dot s2 for singlet and triplet state. Okay, singlet and triplet state given to be minus of 3 by 4 h cross square and 1 by 4 h cross square. Okay, so now you know that there are four possible states, and one is called as a singlet, and three other states are called as a triplet state. Okay, and those triplet state is obtained when the triplet state is obtained by capital S is equal to 1, whereas the singlet state is obtained by S equal to 1. This is the total spin. Okay, now question is also asked, then can you find S1 dot of S2? Okay, so S1 dot S2, that the product of this. Okay, calculate that S1 dot S2 for the singlet and the triplet state given to be this one. Or in other words, we have to prove that S1 plus H1 dot S2 for a singlet is minus 3 by 4 h cross square, whereas for triplet is 1 by 4 h cross square. So how do we do that? We use your concepts. We define. You can write. We define total spin operator capital S is equal to S1 plus S2. Okay, and capital S square is equal to S1 square plus S2 square plus 2S1 dot of S2. This is the term that we have to find it out. Okay, so how do we get S1 dot of S2? We can use the concept of your S square is equal to S1 square plus S2 square plus 2S1 of S2. Okay, now how do you get S1 dot of S2? S1 dot of S2 is equal to S square minus of S1 square minus of S2 square by half. Okay, so if we know the total S square, if we know the total S1 square, S2 square, then we know the value of S1 and S2. And this S square is what? This S square is either 1 or 0. Just like we have obtained for this 0 means for the singlet state, and this one is your triplet state. Right, now what we have to find, you have to find out S1 dot of S2. I mean, we have to just find out what is S1 S2 and then what is capital S square. Then you can calculate what is your S1 dot S2 for your singlet and triplet. So now what is S1 dot of S2 for singlet state? So for the singlet state, what happened? Capital S, remember, is equal to 0. We have already seen for the singlet state, the total spin is equal to 0. That means S1 dot of S2 equal to half. If you look back this formula, if you look back to this problem, capital S equal to half, and then we get 0 square minus. What is S1? This is very, very important. What is S1? S1 square, if you go back to quantum mechanics, we get S1 square is equal to S1 plus 1 h cross square. Right, this is the eigenvalue in which S1 is equal to half plus 1 h cross square. Similarly for your S2 also is equal to S2 plus 1 h cross square. Right, that I think you have already, you already know that this is from your quantum mechanics. And remember capital S square also, capital S square is equal to S plus 1, sorry, S plus 1 h cross square. Okay, so if I have to write, sorry, here this should not be like this, this should be capital S square. What you have to write, you have S plus 1. S plus 1, what is this? S plus 1 means S equal to 0, so 0 plus 1 h cross square. Correct, because for a singlet state, capital S is equal to 0. Now what happens? If you solve this S1 square, you will get minus 3 by 4 h cross square, and again S2 also will be the same, you will get minus 3 by 4 h cross square. Right, so the total will be half minus of 6 by 4 h cross square, which will be equal to minus of 3 by 4 h cross square. Okay, so that is done. Your singlet state, the product S1 dot of S2 gives you minus of 3 by 4 h cross square. And similarly for your triplet state, what happens? Capital S equal to 1. So that means S1 dot of S2 is equal to S plus 1 h cross square. Will get something like 1 plus 1 h cross square. That means you solve this formula. Sorry. You solve this, you use this formula S plus 1 h cross square, because we have to find out eigenvalues, and minus of 3 by 4 h cross square minus of 1 by 4 h cross square. Then what happens, since now this is not S equal to 0, you have S equal to 1 for a triplet state. That is why you will get something like 2 h cross square, this is 1 by half should be there, 2 h cross square, and minus 3 by 2 h cross square. Finally you will get 1 by 4 h cross square. Okay, so if we have to spin, so let's go back. Okay, let's go back. What are the formulas that we use here? Okay, what are the formulas? Suppose if you have two spins, okay, let's say two particles which spin half. Okay, if you combine them together, what are the possible states? There are 4 possible states. You can directly use this equation here. N is equal to 2s1 plus 1, 2s2 plus 1. Okay, you get 4 possible states, and these 4 possible, what are they? Okay, the first one is it can be singlet state when the two spins are opposite to one another, so you have total spin S equal to 0, and when the total S is equal to 0, it's called as a singlet state. And now, or if capital S is equal to 1, then you have 3 possible states, and those are called as a triplet states, 2s plus 1. Okay, this is the number of state, which is 2s plus 1 is equal to 3, with the total spin S equal to 1. Okay, so suppose if you have a singlet and a triplet state, questions also ask what is the possible value of S1 dot S2. Okay, so to find out S1 dot S2, you cannot just multiply S1 dot S2. right? So what you do is that you do these operators here. S is equal to S1 plus S2. Then you square both of them. So when you square both of them, you will have what? It will be A plus B whole square, or A dot B whole square. So I'm sorry, A plus B whole square. Then we get S1 square plus S2 square plus 2S1 S2. Then now you know what this is S1 S2, which proportion depend upon the S square, S1 square, and S2 square. Okay, if you want to have a little more idea about this, you can go back to quantum mechanics. Okay, we have already seen that what is the eigenvalues, right? What is the eigenvalues? If I sorry again, sorry, this internet again is mess up. Yeah, so shit. Yeah. Okay. Again, so sorry. It was raining, and suddenly this internet is giving us problems. So sorry. So sorry about it. And let me just reshare the screen. Let me just go back. It's giving some problem. Cannot do it. Yeah, so sorry, so sorry. This internet is giving me problems. Okay, I think it's so first time I think it is raining here, so so sorry for that. Okay, so yeah, so this is the questions number two, that in which we try to solve what are the possible spin states. Okay, what are the, or the if there are two spin states with spin plus half plus half, if we try to combine it together, and what are the possible and the states that is available. So as we have seen, there are four possible states. One is called as a singlet, in which the total spin equal to s equal to zero, or is called as a triplet state. And we have also seen what is s1 dot of s2. Now for both singlet and triplet, that means what are the values of it. Okay, so in order to do that, we use what we use from the quantum mechanics, which is a squaring of your operators s square. Squaring of the operators s square is equal to s1 square plus s2 square plus 2s1 s2. Okay, then from there, that you can calculate what is s1 and s2 using the value of s plus 1 h cross square. That is your energy eigen, that is not energy eigenvalue, that is your eigenvalues for your Natta spin. Okay, so that we have also seen from your quantum mechanics. So if you want to go back, you can, I think you remember this concept: s is equal to s plus 1 h cross square, angular momentum L is equal to L plus 1 h cross square, correct? L square, and j square is also equal to j plus 1 h cross square. Okay, whatever I have used here as s plus 1 h cross square is from your quantum mechanics concepts. Okay, so then you can substitute what is your value of nata s, your value of, in your case we are using nata s, or if you are using in quantum physics we have done before, we are using your angular momentum also. This is your nata spin, and this is your total angular momentum nata j, and this is the concept that we are using here. Okay, in your nata two spin states. Okay, fine. So that is fine. Then we will go to your let me quickly solve your questions number nata 3 also, not question number 3, questions number 5, nata, which is related to your superconductivity. So okay, when we say a superconductivity, we means that at a certain temperature, okay, at a certain temperature or a certain magnetic field, the resistance goes to zero of a materials. Okay, few elements show superconductivity, few elements does not show superconductivity, and that depends on the nature. Okay, so if you remember, okay, in your maybe in your superconductivity classes, okay, what happens is that there is a concept called critical field. Call your critical field. What is a critical field? Critical field means it is the value of the magnetic field in which below that particular value of field, your materials behave as a superconductors. Otherwise, it will behave as your normal materials. Okay, so that is a critical field, or you also call as a critical temperature. Below a critical temperature, your materials behave as a superconductors, or above that critical temperature, your materials changes into your normal conductor. So if you remember, or if you remember, I can just draw this plot. I think you might have already seen that something like this and something like this, right? So suppose this is your resistance plot, and suppose this is your temperature plot, and this is your critical temperature. So these regions is called as your superconductor. Okay, and this above your TC, it becomes as a normal conductor. Right, that means below your TC, below this region TC, that your resistance suddenly drops to zero. So that is what that is called as the superconductors. And above this, if you increase the temperature, your superconductor loses its nature and becomes a normal conductor. Okay, so here, I mean, other than the critical temperature, there is also a called critical field. Critical field is also the same concept in which below that field, your material behave as a superconductor. Otherwise, you will have what you call as a normal state or a normal materials, normal conductor. Now, the questions number 5 says that for a superconducting, okay, if you want, I mean, example here, let's say, example here for a superconductor, I can also write aluminum. Okay, aluminum is a superconductors. Okay, and gold is not a superconductor. Gold gold is not a superconductor, but aluminum is a superconductor. Okay, there are ways that, I mean, there are explanation why gold is a superconductor, why gold is not a superconductor, why aluminum is a superconductor, and so on. Okay, but for these problems, what we have to find out, what is the critical and the field. Okay, so for a superconducting tin with a critical temperature, so it's given with a critical temperature of 3.7 Kelvin at zero magnetic field. Okay, and a critical field of 0.0306 at Tesla at 0 Kelvin. Find the critical magnetic field at 2 Kelvin. Okay, so what this problem is? This problem is about critical temperature and critical field combined together. As I have just mentioned that there are two critical parameters here. One is your critical field, your critical magnetic field, and one is your critical temperature. Above either critical field or above critical temperature, your material will lose its superconducting nature. It will become a normal material or a normal conductor, in other words. But below this critical field or critical temperature, your material behaves as a superconductor. Okay, that is what it means. And the relation relating both critical field and temperature is given by critical field at a certain temperature is Hc naught, that is the critical field at zero temperature, 1 minus T by Tc whole square. Okay, so remember this formula. H is equal to Hc naught. What is Hc? This is the critical field, temperature is 0. This is critical field at a temperature T, and this is your temperature T, and this is your critical temperature. So these relates and the both your critical temperature as well as the critical field. And now suppose if you reach T is equal to Tc, then what happens? You have Hc, the critical field goes to 0, right? So if I can say, I'll just give you an example. If T is equal to Tc, then what happens? This term is equal to 1, T by Tc will be equal to 1, 1 minus 1 equal to 0, then your critical field equal to 0. That means once you reach the critical temperature Tc, that means your critical field also disappears. Okay, Hc at temperature T is also disappears. That means it becomes a normal conductor. So now what happens is that it is given to you your Hc at 0 Kelvin. So Hc naught is given to you, Hc naught, H critical field at 0 Kelvin is given to you to be 0.0306, and your critical field is also, I mean, critical temperature is given to be 3.7 Kelvin, right? And we have to find out what is the critical field at T is equal to 2 Kelvin, and we have to find out what is 2 Kelvin. Okay, so that means your critical field is given to you. This is Tesla, okay, and your critical temperature is 2.7 Kelvin. Okay, and we have to find out what is the critical field at 2 Kelvin. We cannot find the critical field above, because anyway it will equal to negative or it will equal to 0. But the only thing is that below, this is your maximum. Tc is maximum to 3.7 Kelvin, and for that, at 0 field you have Hc is equal to 0. I mean Hc naught at 0 temperature you have 0.0306, and below this temperature, below your critical temperature, what will be your critical field? That is the question. Okay, that means as you go down in temperature, how does critical field changes. Okay, that is what we have to find out. So the formula is already, you can follow this formula. Hc is equal to Hc 1 minus of T by Tc whole square. Then we substitute Hc at 2 Kelvin. What will happen is 0.0306. You can substitute this is Hc0, and 1 minus of temperature is 2 Kelvin by 3.7 Kelvin whole square. Okay, here I have substituted these values into your main equation. I will name this as equation 1. Let's say I have substituted this in equation 1. Then it's easy now. 0.0306, you can substitute 1 minus of 2 square will be equal to 4. Okay, this is Kelvin, this is also Kelvin. Okay, same unit. That means you will have unitless. So you have 36.69. Okay, and 0.0306 into your 9.69 by 13.69, you will get approximately 0.02 Tesla. You see here one thing which if you note carefully, what is the critical field at 0 Kelvin is 0.03, but as you increase the temperature to 2 Kelvin, your critical field decreases from 0.023 to 0.01. So you see, that means they are related to one another. If you increase the temperature, what will happen to your critical field? The critical field also decreases. Okay, if you decrease the temperature, the critical field also increases. Okay, so that's why they are both related to one another. Okay, that means up to a certain stage, so for a superconducting nature, you need to have both of them below the critical temperature and below the critical field. Otherwise, if you increase the temperature, the critical field also decreases automatically. Okay, through this relation, through this equation, you have seen that yes, at 0, Hc at 0, you have 0.036. But when you start increasing the temperature to 2 Kelvin, because this is at 0 Kelvin, right? At 0.0306 is at 0 Kelvin. But when you increase this to 2 Kelvin, what will happen is that your critical field also decreases. So that is also, that should be there, and that you should note in mind. Okay, fine. The question number, in the same set, the question number B, I will rather say, what is it? Determine the distance from the surface to a point inside the semiconductor in terms of the penetration depth where the magnetic field is 2/3 of its value at the surface. Okay, so if you have, okay, let me interpret this questions. Suppose if you have a superconducting material and you try to apply magnetic field to that superconducting material, it will not go inside it, but it will just penetrate and dies down exponentially. That means it cannot penetrate like you pass let's say a light to any material, or you shine a beam to any material. Okay, it's different. Here what happens is that suppose if you have let me just draw a graph so that it will be easy. Suppose you have a distance and you have this a magnetic field, okay, in the y-axis. So what happens, suppose if you have a magnetic field here and you try to apply a magnetic field to a superconducting material. Let's say this is a superconducting material with a distance x. And how does the magnetic field? The magnetic field cannot just go like this. No, this is wrong. It goes exponentially and dies down. That means as soon as it penetrates the surface, it just dies down exponentially. And this exponentially is proportional to what? E to the power minus of x divided by lambda. Here, this lambda is called as a penetration depth. Okay, the term lambda here is called as a penetration depth. So the question number B says that. The question number B says that determine the distance, determine the distance from the surface. Okay, that means from the surface of your superconducting materials to a point inside a superconductor in terms of penetration depth okay, where magnetic field is 2/3 of its value on the surface. Okay, so this the same question, the same meaning of this question. We have to find out up to what distance in which the magnetic field can penetrate such that the magnetic falls down two-thirds of its value at the surface. Suppose if your value at the surface is b naught, then you have to find out the value inside the surface up to which your magnetic field is 2 by third of b naught. That means you have to find out up to which distance in which the magnetic field reduced drastically from 2 by third of your b naught. Remember that the maximum magnetic field is on the surface, let's say b naught, but as soon as you try to penetrate the superconducting material, it decreases exponentially, and you have to find out that distance, okay, up to which distance magnetic field can penetrate such that the magnetic field reduces 2 by third of its maximum value. Okay, that is the question. And since I have shown it to you that the magnetic field at a distance x is equal to at a distance 0 e to the power minus of x divided by lambda. Okay, where what is here b naught? B naught is magnetic field on the surface, or x equal to 0, whereas lambda here is a penetration depth, London penetration depth or penetration depth. Okay, I will write it here, London penetration depth. Now, if you use this formula, what happens is that you already know what is the magnetic field, how much it reduces. So your magnetic field, it should go 2 by 3 of b naught. Right? You have to find out the distance in which the magnetic field B reduced to 2 by 3 of your B naught. Okay, is equal to the same thing, B naught e to the power minus of x divided by lambda. Correct? So B naught and B naught will get cancelled. So you will have 2 by 3 e to the power minus of x divided by lambda. And since you have exponential here, you can take the log on both sides. So you can take log on both sides, 2 by 3. So log and e will get cancelled, so you have minus of x divided by lambda. Okay, and here you have to find out. Okay, x is the distance in which your magnetic field reduced to 2 by 3 of b naught. You have to find out what is this x. So x is equal to minus of lambda. You can substitute back, that means some lambda ln of 2 by 3, or if you invert the sign, you will have lambda ln of 3 by 2. Okay, if you invert 2 by 3 by 3 by 2, the negative sign will be gone. Okay, now finally, what do you have? You have x is equal to lambda 1.5, because 3 by 2 is equal to 1.5, you will get 0.405 approximately lambda. Okay, that means how much in terms of the London penetration is 0.4 of the London penetration depth, such that the magnetic field reduces to 2 by third of the maximum magnetic field. Or if I want to maybe such a schematic, or maybe I can draw a schematic here, maybe for you to understand for these problems. Suppose the magnetic field is 1, or let's say b is b naught, which is maximum, and this is your bx by b naught. Okay, bx by b naught is the ratio, so you have a unit 1 here. That means your bx and b naught on the surface are the same, okay, which is equal to 1. And you have, let's say this is distance of x, which is proportional of lambda. Okay, so what does it mean? It means that here, since it is decaying exponentially, you can write in this way. Okay, it reduces. And what is this distance? Let's say here, let's say this is 0.5, let's say this is 1, you can write 0.4 is terms of it here. So this distance is 0.405. Okay, and what is the magnetic field? It should be 2 by third of your maximum value. Okay, so this simple diagram tells you that, okay, up to what distance in which the magnetic field decay exponentially, you can calculate it. Okay, up to what distance the magnetic field will reduce by this much. Okay, up to what distance it will be reduced exponentially. Okay, so here your b of x is described by e to the power minus of x by lambda. Okay, that means your magnetic field decrease exponentially as it goes down. As it penetrates inside your superconducting materials. Okay, so and from there you can also calculate what is the distance in which it can penetrate, such that your magnetic field, let's say, reduces by half, or reduces by 2 by 3, reduces by 4 by 3, and so on. Okay, using a simple formula, Bx is equal to B naught e to the power of x squared by lambda. Okay, so I hope you understand about the superconducting nature. If you have any questions, again, we can solve some more questions like in the supplementary sessions. Okay, so that will be in the next coming weeks.
Excuse me, sir.
Yes, hello.
Sir, what about graph between magnetization and temperature for ferromagnetic substances?
Oh, okay, okay. So what is that? What is that questions? Magnetization versus. Oh, okay. So that is question number 4, right? Yeah, yeah. Let me just check. Okay, okay, okay. Let me just check. Uh, okay, so fine. Let me just go back. I think that is question number. Yeah, yeah. Oh, okay, okay, okay. I think this one. I think in the questions number 4, I think you are asking about the magnetization versus temperature, right? Yeah. Okay. So another question is, sir, I asked one question. Our assignment is subjective. Then what is the exam pattern? Oh, okay. So related to your exams, okay, I am not like in charge of exams, but I can ask to the uh, uh, like higher authorities who are dealing with the exams patterns. So see, I'm not at the moment, we are not the one to set to the questions. Okay, we are one to help you how to solve the problems. Okay, relating to your exams, I can ask I mean, from higher authorities what is the exam pattern, but uh, I think from my side, I think it's more related to whatever the assignments, okay, whichever we are done in the class, okay, related. But I have to ask, okay, this particular exam pattern. So sorry, I have to get more information. Okay, yeah, okay, so I can get back to you maybe in the next class. Okay. Uh, yeah, okay. I'll get back to you in the next class. Okay. I'll ask the higher authorities by this week. Then I can get back to you. Fine. Okay. So the last question was how does your magnetization versus temperature curve? Okay. For a ferromagnetic material, that uh, yeah, yeah. Okay. So I will not be able to derive, but I will just show it here. That means I will just show it here. I'll show it here. So here, this is your magnetization, and this is your temperature T. Okay. So what is usually the pattern? The pattern is that your ferromagnetic and the material in the ferromagnetic material, your magnetization, it decreases with temperature. Okay, so that is one point that you should take into account, that the magnetization decreases with temperature. So that means there is a transition. Okay, so if you want to go into detail, you can follow from Kittel's book, but I can write your M is proportional to something like uh, T minus of T to the power of beta, somewhat of this form. That means your temperature, your magnetization should decrease with the temperature. I mean, your magnetization should decrease with the temperature. So if I can draw, it will be some sort of, sorry, what am I doing? Something like this, something like this. Okay, in which this is your Tc. That means once you reach a critical temperature, your magnetization equal to 0. Because from here, from this formula, T minus of Tc, that if T is proportional, if it's equal to Tc, then your magnetization will be equal to 0. So this is M at T equal to 0. You have the maximum, you have to have the maximum temperature. But if you increase the temperature, what will happen is that your magnetization starts decreasing. Okay, so this is M versus temperature T. Okay, if you want to go more into detail, yeah, I can suggest you the Kittel's book, but for these problems is just draw the magnetization with versus temperature curve, so you can follow this type of structures. Okay, fine. Now I have two more problems to finish. Then maybe we can stop. Two more problems, yeah. So that is the question number 2 and question number 3. Okay, so question number 2 and question number 3. Let me solve first the question number 3. Okay, so I have already solved question number 1, question number 4, question number 5. So question number 3 is more like Yeah, about paramagnetic, if I'm not wrong. Yeah, I think paramagnetic. Yeah, okay. So the question is dy 3 plus has outer electronic configuration. Okay, calculate the magnetic susceptibility. Susceptibility of the cell sorry, of the cell. Just a second, please. Okay, so yeah, so of the cell, 1 kg mole, 1 kg mole of dy 3 plus ions at 300 Kelvin. Okay, that we have to find out what is the magnetic susceptibility. Okay, this is also the question's magnetic susceptibility, and is given to you is given at the dy at the 3 plus and so on. Okay, so it's just given to you only dy 3 plus. Okay, so we have to calculate what is the magnetic susceptibility. Just 1 minute, please. Okay, just 1 minute. Give me 1 minute. Yeah, okay. So in case, so how do we solve this paramagnetic? We have to solve. Let me just give you the formula. Okay, uh, for your uh, for your paramagnetic, psi m is equal to mu naught n mu effective square by 3 kb t. Okay, so this is the formula for your the magnetic susceptibility of a paramagnetic and the ions. Okay, we have seen your diamagnetic is different. We have seen your diamagnetic is negative. So here for a paramagnetic we have n mu naught and the effective square by 3 kb t. Okay, so this is for your paramagnetic materials. Again, the derivation is there in your Gittle's book or any other standard books. They have all this method derivation. Okay, so now from here, what do we need to find out? We need to find out what is your mu effective. Okay, kb, you know your temperature is already given you at 300 Kelvin, and you have to find out what is your mu effective, which is your yeah, which is the magnetic moment. Okay, mu effective, which is a magnetic and the moment. Now and for yeah, and in order to do that, we have to look at the electronic configuration of dy 3 plus. Okay, so I can solve that by looking at your electronic configuration. So electronic configuration of dy 3 plus is xenon 4f9. Okay, that means there are 9 unpaired electrons in your dy 3 plus. Okay, this is your xenon. Okay, and for f9. Okay, so this is your electronic configuration. You have to expand all your the dy 3 plus electronic configuration, and you will see that you will get the xe the 4f to the power 9. That means that means there are 9 unpaired electrons, or 9 in the outermost shell. I will say not unpaired electron. I will say there are 9 electrons in the outermost shells. Okay, now for your 4f soft shells, for a 4f soft shell, what is the angular momentum? L equal to 3. How do you get that? You know that SPDF. So for S, L equal to 0, for P, L equal to 1, for D, L equal to 2, and for F, L equal to 3. So since it is we are talking about the 4F soft shell, we are talking about the angular momentum L, quantum number L is equal to 3. Okay, that means what happens? What are the two possible? The total quantum numbers L and the angular momentum quantum number L is equal to 3, and 2L plus 1 equal to what? Equal to 7, and you will get 7 orbitals. with magnetic number 1, with magnetic number 3, 2, 1, 0, minus 1, minus 2, and minus of 3. Okay, so that means what happens in the for the 4f soft shell, your angular momentum L equal to 3, and if you expand this one, you will have 7 orbitals given by this is your possible L value, which possible ML value 3, 2, 1, 0, minus 1, minus 2, minus of 3, and so on. Okay, so that is you get from 2L plus 1, which is equal to 2 into 3 plus 1, we get 7 orbitals. Okay, so if I have to, and let's say, let me just draw it, that if you just draw it for your understanding, it will have some point this way: 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7. So here ML is equal to 3, 2, 1, 0, minus 1, minus 2, and minus of 3. Okay, so there are 7 orbitals now, but there are 9 electrons. Correct. So there are 9 electrons, and there are 7 orbitals. That you can keep in mind. So now what does so we can follow how does the electrons can fill inside the 7 orbitals, because there are 9 electrons and now there are 7 orbitals. So you can use the concept of Hund's rule, okay, which says that the first 7 electrons will occupy the first orbitals. Okay, the first electrons will occupy each orbitals with spin half. So what I mean is that you can write here 1, 2, 3, 4, 5, 6, 7. Okay, with the spin half. Okay, they will first occupy, then the next will be 1, 2. Okay, so the first 1, 2, 3, 4, 5, 6, 7, and the remaining 2 electrons will occupy the first orbitals. ML is equal to 3 and 2. Okay, so if you take the summation L is equal to summation of ML, that means the total angular momentum, what will happen? Why do we need this one? Okay, remember, why do we need this capital L? Because remember, we have to find the total angular momentum, mu effective. So let me just give you an idea of mu effective. Mu effective is equal to GJ, Landis factor, J plus 1 mu B square root. Okay, why do you have to do this L? Why do you have to do all these things? Because we want to find out what is the total angular momentum J, and J is equal to L plus of S. Okay, so let me just remind it here. J is equal to L plus of S. Why do you have to find L? It's because we will see that you need the value of J at the end. That is why we have to solve what is the value of L. Okay, so now how do you get the value of L? You get the value, you know that there are 7 electrons, and these electrons are arranged according to Hund's rule, and then capital of L is equal to summation of L. That means you just need to add here. So we get how many electrons in 3? You will have 1 is to 3 initially, 1 into 3 plus 1 into 2 plus 1 into 0 plus 1 into minus 1 plus 1 into minus 2 plus 1 electron into with the ML minus equal to 3. Then finally what happens? Plus again 1 more electron here, 1 into 3 plus 1 into 2. Okay, so if you do this and anyway this cancel with this cancel, 2 and 2 will cancel, 0 is equal to 0, 1 equal to the remaining, you have ML is equal to 5, 3 plus 2. Okay, and similarly capital letter S, how will be capital letter S is equal to summation of MS. What is summation of MS means? How many number of spin half are there now? These anyway will get cancelled because plus half and minus half are already cancelled. Plus half and minus half are already cancelled. You have 1, 2, 3, 4, only 5 more. So you have 5 into spin half. You will get 5 by 2. Okay, now you know both S and L. Then we have J equal to L plus S, which is equal to 5 plus 5 by 2, which is equal to 15 by 2. Okay, so so now once we get that, we can calculate. If you look back at the formula, you get what is the value of J, you already know. Now you have to calculate what is the value of GJ. GJ is the Landis factor, which is given to be 1 plus J plus 1 plus S plus 1 minus of L plus 1 divided by 2J plus 1. This is the formula if you have to find out the Landis factor. Okay, you know what is a G factor, but this is for a total angular momentum. You have a concept of Landis factor, which is given by the total angular momentum J, spin angular momentum, orbital angular momentum, and so on. Here, what happens? S is you know, which is equal to 5 by 2. L you know, which is equal to 5. and also J is equal to 15 by 2. Okay, once you know this, you substitute back in this equation. You substitute back in that equation, and you get Gj equal to 1 plus J is 15 by 2, and instead 15 by 2 plus 1 plus, what is the spin? Spin is 5 by 2, so 5 by 2 again, 5 by 2 plus 1, correct, and minus L is equal to 5 and 5 plus 1, correct, and divided by 2 into 15 by 2 and 17 by 2. Okay, so you just substitute what is the L, J and S, and I will not solve, you can solve, you will get something like 4 divided by 3. Okay, after solving this one. Finally, your effective magnetic moment mu effective is equal to Gj, you already know, 4 by 3. You use this formula. Let me just write it, that will be easier. Let me Gj is equal to Gj root over of J plus 1 Bohr magneton mu B. Okay, so Gj you know 4 by 3, J is also you know 15 by 2, and J 15 by 2 plus 1 will get 17 by 2 mu B, and this term is approximately 10.6 mu B. Okay, so once we know that, you can calculate now your main formula. We get psi m equal to mu naught n, okay, n mu effective square divided by 3 kBt. Okay, now you can substitute back your final equation, which is equal to mu naught, you know, which is equal to 4 pi into 10 to the power minus of 7 in the SI unit terms. So n is equal to 1 kg mole, right? Because question is already given to you, n is equal to 1 kg mole, which is equal to 1 kg is 1000 grams into Na is 6.023 into 10 to the power 26. Sorry, into 10 to the power 23. Sorry, that's not 26, this is 10 to the power 23, which is approximately equal to 6.02 into 10 to the power 26 kg mole. This is in terms of kg, which is equal to 6.023 into 10 to the power 26 ions. Okay, so now you know what is the value of n. Temperature is also, you already know, 300 Kelvin, and what you can just substitute, we can just substitute back. Psi m is equal to mu naught is 4 pi into 10 to the power minus 7, right, into Na, you already know 6.023 into 10 to the power 26, this is the number of ions, into what is your mu effective square, right, your mu effective square. You can just substitute your mu effective square here. There's your mu effective square divided by 3 into kBt. Okay, so 300 Kelvin, and this is your kb, this is your temperature. Okay, and you substitute what is the value of mu effective square that you get from this formula, and remember that mu b equal to 9.27. remember, 10 to the minus 24 joule Tesla inverse. Okay, you substitute what is the value of mu effective and also substitute value of mu b, you will get approximately equal to psi m equal to 5.93 into 10 to the power minus 4 per meter cube. Okay, so approximately you get, so you can do that calculation. Okay, you can do the calculation, you can just substitute the values and then do the final calculation. And finally, for 1 kg mole, let's say for 1 kg mole in the SI unit, you will be talking about something like approximately 5.93 into 10 to the power minus 4 meter cube kg mole inverse. Okay, so for these problems, okay, that is it's not that difficult. It's just like you just need to calculate what is your mu and the effective square, and then you just substitute back in the temperature is already given to you, n is already given to you. What you need to calculate is only the mu effective, okay, which is the magnetic moment, and the magnetic moment is related to your orbital and angular momentum. I mean, orbital angular momentum and spin angular momentum by the relation I have given to you, this relation. Mu effective is equal to Jj plus 1 mu b, where J is the total angular momentum. So if you want to find out the total angular momentum, you have to first find what is the spin and the orbital angular momentum, then add it up. J is equal to L plus S. Okay, fine. Now I will do the last problems. Okay, I have 20 to 30 minutes. I will do the last problems. Yeah, so this is a little bit, yeah, okay. So I will do the last problem. So question number 2, which is your paramagnetic gas. So what is given in the question number, is given that a paramagnetic gas with L equal to 0, remember, and S is equal to half, contains n atoms per meter cube. Okay, so there are n atoms per meter cube with L equal to 0 and with S is equal to half. Okay, that is the question. And the question is, obtain the atomic densities and the possible energy levels and result magnetization. So there are three of them. One is your atomic densities, second is your magnetization. Okay, that we need to find out. Okay, so now for paramagnetic gas with L equal to 0 and spin equal to half, what is the total angular momentum? J is equal to L plus of S, which is simply equal to half, right? And what is your value of mu is equal to minus of G J mu B J. This we know. So here GJ is the anyway GJ is your Landry factor, and your, since L equal to 0, GJ is the same thing as spin. Remember this, because since L equal to 0, so GJ, whatever the equation that we have used with 1 plus a JJ plus 1 is not required, because it's the same thing as whatever the spin that you have. Spin, the G factor for spin is equal to 2, so whatever GJ is also equal to 2 since L equal to 0. Okay, you don't need to solve. Now, since your GJ is equal to 2, and also your L equal to and spin half, and S is also half, so MJ is equal to plus half and minus of half. Okay, so L equal to 0, GJ is equal to 2, spin is equal to half, you have MJ plus half and minus of half. Now, so that is one thing. Now, what happens if your it's you have an external magnetic field? So in your external magnetic field, the interaction energy is equal to minus of mu dot B. Okay, so when you place in an external magnetic field, what happens to your magnetic moments? What happens to the interaction energy? I mean, the interaction energy will be given by the product of your magnetic moment that you have into your magnetic field B, which means that minus of mu, you can take it from here. Minus of mu is already given here, G J mu B J, which is equal to mu. You can take something like MJ GJ mu B B. Okay, so that means this is your energy. Okay, so fine. Why do we need this energy term? Okay, you will see very soon why do we need this energy. So how does energy is equal to minus of mu dot B? This is B and this is mu. You just substitute mu is equal to minus of what? Minus of GJ mu B and J, right? Fine. Now for that, for MJ equal to half, E plus will be simply what? This is equal to 2, this is equal to half, so it will get cancelled, will be simply mu BB. This is anti-parallel, this is called anti-parallel to magnetic field B. Whereas MJ equal to minus of half, we have E negative is equal to minus of mu B, which is parallel to B. So what does it mean? It means that when you apply magnetic field, so there will be two types of, there will be two energies. Okay, one is those ions which are aligned parallel to the magnetic field is given by this interaction energy, and those ions, okay, or those spins which is aligned anti-parallel to the magnetic field will have this energy minus of mu B. Okay, so that means there are two, you can see there are two energy levels, I can just say. Now, how do we find out the atomic density? This is very important. Okay, how to find out the atomic density? Atomic density is the number, is indirectly is the number. Okay, is the number of atoms, I can say. Now atomic densities is the number of the atoms per unit volume. So atomic densities, I can write it here. Atomic densities is related to your number of atoms per unit volume. Okay, so according to Boltzmann statistics, n, okay, n, the number of states is proportional to e to the power minus of e divided by kBT. Remember, so n minus is equal to some constant c equal to e to the power minus of e divided by kt, and n plus equal to c e to the power minus of e again divided by kt. So why we need energy term is because according to Boltzmann statistics, the number of atoms is depends upon your energy also. Okay, according to the Boltzmann statistics, this is called also Boltzmann statistics. Okay, so that is why once you know the value of energy, you can substitute here. E plus is mu bb and E minus is minus of mu bb. Then you can directly know what is your n minus. Your n minus will be simply n minus is equal to c e to the power, instead of energy you can substitute what energy that you get from above, mu b by kt, and again n plus will be equal to c e to the power minus of mu b by kt. Okay, so now you know how many number of atoms are there in the with n minus, and how many number of atoms are there with this energy E plus. Okay, so this is the number of atoms with energy E minus, this is the number of atoms with energy n plus. But since n, the total number of atoms will be always n minus plus, will be always equal to the sum of n minus to n plus. So what happens, we get n equal to, we can take this n minus and you can add this one n plus, you can write c, you can write e to the power of mu b by kt plus e to the power minus of mu b by kt. Okay, and this equal to what? This is equal to, you can write this, e to the power x plus of e to the power minus of x, because something 2 cos hyperbolic of mu b by kt n, and this is 2c cos of hyperbolic. So now if you want to find out the constant c here, you can write c equal to simply n by 2 cos hyperbolic mu b by kt. Okay, so now you substitute back what is the value of c, and you get what is atomic densities, because atomic densities is a constant c. And how do you find the constant c? We use this condition. We use the condition of that the total number of atoms per unit volume is the same thing as n minus plus of n plus. Okay, it has to be the same. Okay, because it has to be conserved. That is why you can calculate what is the value of c. So substitute back, we get n minus equal to, you can substitute the value of c with this equation. You can write n e to the power of mu b by kt divided by e to the power of mu b by kt plus of e to the power minus of mu b by kt. Whereas in the case of your n plus will be equal to n e to the power minus of mu b by kt. The only difference between n minus and n plus is this negative sign. Here is positive sign and the other one is negative sign because of your energy. Okay, that's it. Otherwise they are the same. So we get e to the power of mu b by kt plus e to the power minus of mu b by kt. Okay, if you have any confusion, anyway, I will upload the notes whatever I have written. That's all. Okay, you can then refer it much more than the details. But in this case, how do you find the atomic densities? We use the Boltzmann statistics. The Boltzmann statistics says that the number of particles is proportional to e to the power minus of energy by kt. That is why you have to find out. Suppose if it is given to you that the number of, let's say, atoms, you have to find out what is the interaction energy E. Once you know that, then you can substitute it in the value of energy E and you can find the number of particles. And how do we get the energy E here? It's through the interaction energy of magnetic field minus of mu dot of B. Okay, so mu, you know, GJ right, and your magnetic moment, and you can substitute it directly. So the last one, yeah, so last one, I think this is the number densities, right? And the second one we have to find out, let me just check. The second one is, okay, the second one is we have to find out the resulting magnetization. Sorry. So in the same problem, you also have to find out the magnetization. So magnetization is simply n mu b, you know, magnetic moment per unit volume, right? As I've mentioned to you from the very beginning itself, what is magnetization? Magnetization is magnetic moment per unit volume, and you can simply write, you can add up this, you can write mu b tan hyperbolic of mu b by kt. Okay, that is the same, it's just mu b. You add these two terms, okay, your n minus and your n plus, and you will get what is your magnetization. Now, and the second problems, the second section of your problems is given to be if the gas contains 10 to the power 28 atoms, okay, per meter cubed. Calculate the population of the level and the magnetization at 300 Kelvin and 5 Kelvin. Okay, so what you have to find out, what is the populations of the level, okay, that is n minus and n plus. Remember, there are two energy levels now because of the two energies, E plus and E minus. You have two energy levels, n minus and n plus, and also at magnetizations at a magnetic flux density of 2.5 Tesla. So you have to find out what is, so the idea is you have to find out what is n plus, you have to find out n minus, okay, at T equal to 300 Kelvin, 5 Kelvin, at B equal to 2.5 Tesla. Okay, that you need to find out. So for that, you can use the formula which we have already solved. That means, first let's solve this mu b by kt, because since it's always there in your term. So at 300 Kelvin, what happens to mu b by kt? I can represent this as x, that will be easier. So x at 300 Kelvin will be mu b, 9.27 into 10 to the power minus 24. Magnetic field is already given to you, 2.5 Tesla, right, divided by k is 1.38 into 10 to the power minus of 23, and temperature is 300 Kelvin. This you get something approximately 0.005 approximately. Now once you know that, n negative, you can easily calculate what is n negative. N negative is n, and also you have this relation mu b by kt, and e to the power of mu b by kt. So if I want to write it, I can simply write n minus equal to n e to the power of x, plus e to the power of x, right? And x you already know from this one, right? So you substitute n is also equal to 10 to the power 28, is already given to you, 10 to the power 20 e to the power of x, plus of e to the power minus of x. And how do you get x? X is 0.005, and this is equal to approximately 5.02 into 10 to the power 27 per meter cube. Okay, so that is n minus. Similarly, n plus, you do the same thing. N plus is the same thing. So n plus, you get approximately 10 to the power 28 e to the power minus of negative. There's a difference, only the negative sign, e to the power plus x and e to the power minus of x. This is approximately equal to 4.97 into 10 to the power 27 per meter cube. Okay, so that's it. So the question is that once you know n plus and n negative, which we have already derived, they have given it to you what is the number of atoms, and then you can substitute what is the value of your lambda mu b by kt at different temperatures, right? If you look back, what is your n plus and n minus? This is the equation, n plus and n minus. And for this equation, you need to know only n and only the temperature, because everything are, and b, and magnetic field b. Once you know these two terms, these three terms, you know how to calculate n minus. And t is already given to you, magnetic field is already given to you, n is already given to you, and you just substitute in this equation n minus, and you get the total n minus and n plus. And similarly, okay, here you also have to calculate what is the magnetization. Magnetization is also here n mu b tan hyperbolic of mu b by kt. That means if I want to write in terms of x, we get n mu b tan hyperbolic of x, right? So again, you know what is the value of n, you know the value of mu b, which is equal to 9.27, or let me just write it, 10 to the power 28 into 9.27 into 10 to the power minus of 24, and tan hyperbolic of 0.0055 something, and this is approximately equal to 518.98 inverse. Okay, so this is pretty straightforward once you know what is n positive and n negative, and you just use the formula which is already there. Now this is at, remember, this is at 300 Kelvin. The same thing you do at T equal to 5 Kelvin. Okay, what is happening to T at T is equal to 5 Kelvin? So x5 at 5 Kelvin is 9.274 into 10 to the power minus 24. Magnetic field is already given you. Use the same formula, okay? Mu b by kt, 1.38 into 10 to the power minus 23 into 5 Kelvin. Here temperature is equal to 5. This is approximately equal to 0.335. So once you know this x5, you do the same thing. You substitute back in n minus. You will get approximately 5.83. I will not derive it, as not substitute. You can substitute it. It's the same thing. 10 to the power 27 meter inverse. Similarly, n plus equal to, let's say, 10 to the power 28 e to the power minus of x divided by e to the power of x plus of e to the power minus of x. Okay, this x here is this term here coming from at t equal to 5 Kelvin, because x at 300 Kelvin is different. Here x, which is equal to mu b by kt, is different at the temperature 300 Kelvin and the temperature of 5 Kelvin, right? So here you have to substitute the x for 3 Kelvin, because we are calculating at 3 Kelvin. So you have 4.16 into 10 to the power 27 meter inverse, meter cube inverse. Okay, and similarly m also, you have 10 power 28 into 9.274 into 10 to the power minus 24 into tan hyperbolic of, at x is equal to 5 Kelvin, you have this 0.335, and this is approximately equal to 3. Okay, you can just cross check the calculation, but I hope it should be correct. It should be more or less correct. So 1 2 3, yeah, sorry, it should be only 1, sorry. Okay, 0.6. Okay, a meter inverse. So for these problems, okay, this is little bit lengthy. Okay, I will upload the okay, whatever I have calculated in the drive. But for this problem is slightly lengthy, because first of all, you just need to understand how do you get the number of particles in both two states. Okay, that is n minus and n plus. How do you get that? Because you find out the interaction energy. E is equal to minus magnetic moment dot magnetic field. Once you know that there are two energy states, E plus and E minus, you use the Boltzmann statistics to calculate how many number of particles are there, because number of particles is equal to E to the power minus of mu b by kt. Okay, that means you know what is n plus and n minus. So once you know the value of n plus and n minus, you just need only the temperature, magnetic field, and n to calculate what is the value at different temperature. Okay, so the idea, the logic is that first find out what is the energy. First find out what is the energy, and then once you get the energy, you can calculate what is the number of particles. Okay, both n plus and n and the minus. Okay, and once you get that, you go back to the you go to the Boltzmann statistics, in which you can calculate what is n plus and n minus. And once you get the n plus and n minus, you can calculate what is your the values, how many number of particles are there. And for that, you go back to this relation, and to calculate n plus and n minus, you go back to this relation. What is there? The values that you need is what? Is only temperature, magnetic field, and n. And since in the question number 2, n is already provided to you, temperature is already provided to you, 300 Kelvin and 5 Kelvin. For two cases, okay, case 1 is 300 Kelvin, case 2 is 5 Kelvin, and magnetic field is already given to you, 2.5 Tesla. So there it's just numbers, plug it in n plus and n minus. As well as magnetization also is the same thing. You have only magnetic field B, you have temperature T, and n. Mu b is a constant, it's a Bose magnetism, which is 9.27 into 10 power minus 24. Okay, and these are all tan hyperbolic, and you can substitute, and you will get what is the value of magnetization also. So I think for this this sessions, I think is over. I covered like all the 5 questions in the assignments. Okay, I will upload also whatever maybe these notes and whatever I have solved. I can just upload it in the drive, and you can have a look. And any questions also, we can also solve more questions. I mean, if we have time, we can also solve more questions in the supplementary sessions if you want to attend. Okay, I can solve some more questions and there also. But for this part, okay, there is on mostly like a magnetism part. And if you want to go like much more details into it, I think Kettle textbook also provides a lot of ideas and and problems. That is also a good way. And anyway, so if you have any question, you can always mail me. Okay, I'm very happy to try to solve. And Any more questions we can always solve in the supplementary sessions, maybe after 1 or 2 weeks time, okay, when they schedule. Okay, so I think thank you so much for attending the classes. Okay, so sorry also for the internet problems halfway because of the power supply issue. Anyway, I will see you next week, and thank you so much, and thank you all.